Calculus, Chapter 3, Section 1, Exponential Functions. First of all, just to remind you, an exponential function is a function where f of x equals a to the x, where x is any real number. A has to be greater than 0 but cannot be 1. A is called the base. Remember, it's called an exponential function because x is the power. It's the exponent. Here are some examples: 2 to the x, 1/2 to the x, 0.4 to the x. Of course, the power can be a little more involved than just plain old x, but these are the basic types of functions. Here's an example of the graph. When your base is greater than 1, it's positive and increasing. It's a continuous function, which means it's going to be differentiable over the entire domain. It is concave up, which means that the second derivative will always be positive, at least for the base function. And we have x as a horizontal axis. When a is a number between 0 and 1, it's positive, it's decreasing and continuous. It is concave up. So again, the second derivative will be positive. And as x gets larger, the function approaches 0. X is again the horizontal asymptote, x-axis. Now, we're going to define e. E, in case you ever wondered where it came from, was actually defined using limits. It is the limit as h approaches 0 of 1 plus h to the 1 over h power. And if you keep putting in numbers that are smaller and smaller and smaller, you get this approximation here. E is an irrational number like pi. It goes on forever and does not repeat or repeat a pattern or ever end. E is called the natural base. The nice thing about E is it's very easy to work with in calculus. Theorem 1 says that the derivative of the function f given by f of x equals e to the x is e to the x. The derivative of e to the x is e to the x. That's it, plain and simple. And we are only going to be working with e to the x. We're going to be working with e as our base. Okay, so some examples. Now, I will warn you, we do need to bring into play for b and c. B, we need the product rule. C, we need the quotient rule. Pause the recording, give these a try and resume to check your answer. Okay, for a, 3e to the x, the derivative is 3e to the x. Very simple. For b, we do need to use the product rule, so we have the first times the derivative of the second, plus the second times the derivative of the first, so x squared e to the x plus e to the x times 2x. And then you can leave it like that, but they did, in this answer, factor out the e to the x. That is not necessary, but you can do it if you so choose. And then finally, we need to use the product rule, which is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And here you'll notice again, they did factor out the common factor, this time both x squared and e to the x, and they were able to reduce the fraction just a little bit. Okay, theorem 2 tells us that the derivative of e to some power is the product of e to that power and the derivative of the power. This is actually our chain rule. In other words, when your power is more than just x, if it was something like 2x plus 3, the derivative of e to the 2x plus 3 would be e to the 2x plus 3 times 2. The extra 2 is the derivative of the power. So you do e to the power times the derivative of the power. That works. Okay, try these out. Remember, what you're going to do, it's going to be e to the power times the derivative of the power. Pause the recording and give these a try and resume to check your answer. Okay, so e to the 8x. So our answer is e to the 8x times the derivative of 8x, which is just 8. So 8e to the 8x. For b, again, e to the negative x squared plus 4x minus 7 stays the same, and then we multiply that by the derivative of negative x squared plus 4x minus 7, which is negative 2x plus 4. And they factored out a little bit here. You don't need to go that far. Do make sure, though, that I can tell the difference between your power and what you're multiplying there. It's really important that I'm able to tell the difference when you write it. So those of you whose writing tends to be a little bit on the shaky side for testing quizzes, be really clear about that. For C, first of all, what we did is we changed the power to x squared minus 3 to the 1/2 to make it a little easier. So it's e to the power of x squared minus 3 to the 1/2 times, now we're going to do the derivative of x squared minus 3 to the 1/2, which is 1/2 x squared minus 3 to the negative 1/2 times 2x. Notice we're using the chain rule twice. I compare the chain rule to M&Ms because you want to do the candy shell first and then the chocolate. This is kind of like doing a peanut M&M. Okay, the candy shell is the e to the x, the chocolate is the 1/2 x squared minus 3 to the negative 1/2, and then the peanut in the middle is the 2x. You just take it one layer at a time. And then you can see that they did some simplifying. You don't really need to mess with that, although you can if you would like to. Okay, so here's an example. It's reasonable for a manufacturer to expect the daily output of a new worker to be low at first and increase over time and then level off. A firm that manufactures 6G smartphones determines that after T working days, the number of phones produced per day by the average worker can be modeled by, and you have the function here. So A, all you're going to do is put in 0, 1, 5, 10, etc., and get those answers. You're not taking a derivative there, you're just putting those numbers in. B, you're just going to graph that function. C, you are going to take the derivative. And D, you're going to find critical values. Now remember what that means is you're going to set C equal to 0 and solve and figure out where the graph, according to the first derivative, is increasing and decreasing. You're going to find the second derivative and any inflection points, and then what number of phones seems to determine where the worker output levels off. So after how many phones do things seem to even out? All right, pause the recording, give this a try, and resume to check your answer. Our values. And then B, they basically just used the A to graph it, or you can use your calculator. And it looks like if you continue out the pattern, it levels off at about 80. Okay, so for C, taking the derivative, we have negative 70e to the negative 0.13t times negative 0.13t, which is 9.1e to the negative 0.13t. So that is the rate of change. This is greater than 0 because you can't, e is a positive number, you can't raise a positive number to a power and get a negative. So the whole thing is positive. It doesn't matter what t is, it's going to always be positive. So the entire graph is increasing. There are no critical values. We already said that, now in this case it's a little different because we have the negative power. If you take the second derivative, we get negative 1.183e to the negative 0.13t. That is going to be negative over the entire graph. There are no points of inflection, and it is concave down over the entire graph. And the worker, and it looks like it levels off at about 80 phones per day. So in other words, once they get to about 80, they're really not going to improve upon that anymore. All right, here's a summary of what we just talked about. So if you will pause the recording and look over this, and then resume and do some practice problems. Okay, as you go through these, pause the recording, give these a try, then resume, check your answer, and continue this way through the rest of the recording.